In section 3.9, you will learn about differentials. First up is tangent line approximations. In this example, suppose that f of x is equal to x to the fourth, and we will let t of x be the tangent line at the point 381. And we have to find the equation for t of x. So t of x is this line right here. We know that to find the equation of a line, we need two items. We need a point and a slope. Now, the slope of the tangent line at the point 3,81 is going to come from f prime evaluated at x equals 3. If f of x is x to the fourth, then f prime of x is going to equal 4x to the third. Then that means that f prime of 3 is going to equal 4 times 3 to the third, which is 4 times 27, which is 108. So it's a very steep slope, which makes sense with how the graph looks here. Now we know that point-slope form of a line is y minus y1 is equal to m times x minus x1. And now we can plug in. We have y minus 81 is equal to the slope, which we said is 108 times x minus 3. If we distribute, we then have y minus 81 is equal to 108x minus 324. And if we add 81 to both sides, we have y is equal to 108x minus 243. So this gives us our tangent line approximation. T of x is equal to 108x minus 243. In this next example, suppose we zoom in at the point of tangency 3,81. We're going to look at x values that are near x equals 3. We've got a table of values here with the actual value of the function. We also plug in all those x values into t of x, which gives us an approximation for the function. So what's happening here is we see at the point of tangency, the approximation is perfect, meaning there is no error there. And as we go a little farther away, say to 3.01, we see the actual value of the function would be up here, and that's the 82.08541, whereas t of x is giving us an approximation right here with a y value of 82.08. And it's important for you to understand that this error right here is representing the difference between the actual function value and the tangent line approximation. And over here on this picture, that means it's the difference between this y value and this y value. That is the error. So what I want you to do right now is pause the video and go grab your calculator and then find the error in the approximation for each of these four values, and then answer this question down here. And after you do that, then turn the video back on and we'll continue our discussion. So go ahead and pause the video now, fill in these values, and answer the question. At x equals 2.9, the error was 0.5281. At x equals 2.99, the error was 0.00539. At x equals 3.01, the error was 0.00541. And at x equals 3.1, the error was 0.5521. So what we notice is as x gets farther away from the point of tangency, so farther away to the left or farther away to the right, we see that the error gets worse. So the conclusion that we can make here is that the tangent line approximation is best for very small changes in x. So the tangent line approximation is much simpler to calculate than the actual function, particularly when you start plugging in x values that have more and more decimal places. If you were doing those by hand, taking x to the fourth when x is 2.99 is a lot more arduous than just plugging 2.99 into a linear formula. So we like using the tangent line approximation. We have to just understand that its limitations are we need to keep those x values close to the point of tangency so that our accuracy is better. Next up is differentials. So consider this diagram here where we have f of x, which is the curve. We are going to pick a point which is x comma f of x. Let's draw the tangent line in there. And then from x, we're going to go over a small distance, delta x, which means this x value is x plus delta x. If we go up to the function, then the coordinates of this point are x plus delta x, comma, f of x plus delta x. Now from the point x f of x to this new point, the change in y value from here to here, that change is the actual change using the function, and we call that delta y. And so to find that, we just do the y value of this second point and subtract away the y value of this first point. Now, consider the tangent line here. We know that it goes through this point, x f of x. We know that it will go over by the same amount as the function value, x value, goes over. But when we take this new x value and bring it up to the tangent line, we see that the y value is different than the y value of the actual function. Now we call this difference between the y value from the tangent line and the y value of the original point dy, which is the approximate change using the tangent line. Now notice on the tangent line, the x value changes exactly the same amount because we are in control of that. So we call this distance from here to here dx. And you notice that dx is exactly the same as delta x. So the change for x in the function is exactly the same as the change for x in the approximation. What's different is that dy is different from delta y. This is delta y, that's the actual change in the y value. This is dy, which is the approximate change using the tangent line. But what we do is we use dy to approximate delta y. And this is the concept of differentials. In differentials, we use dy to approximate delta y. And that's what we just wrote, that dy is approximately equal to delta y. And as delta x gets smaller and smaller, the difference between dy and delta y gets smaller and smaller. In other words, the error gets less and less. Now, if we consider that the slope of the tangent is equal to the derivative at any point, well, we know the slope of this tangent line right here, this red tangent line, is going to be y2 minus y1 over x2 minus x1. Well, the change in the y values is dy. The change in the x values is dx. Remember, we're talking about the tangent line here, not the actual function. So the difference of y values is dy, that's why that goes in the top, and the difference of x values is dx in the denominator. And that has to equal the derivative, which we know is f prime of x, which also gives us the slope of the tangent line here. What we can do is think of this algebraically. We're going to take this dx and cross multiply it up and write this as dy is equal to f prime of x dx. And this is called the differential of y. Now, in this example, we have to compare delta y to dy for f of x equals x squared plus x plus 1 at x equals 2, given that delta x, which we know is equal to dx, is equal to 0.1. Now, delta y, we know, is going to be f of x plus delta x minus f of x. So if we plug in here, we will get f of, remember, x is equal to 2 plus delta x is given to be 0.1, and then we have to subtract f of x, which will be f of 2. Simplifying, we have f of 2.1 minus f of 2. Now, if we calculate these values, we take 2.1 and plug it into this function, we're going to get 7.51, and we have to subtract away f of 2. If we put 2 into the function, we get exactly 7. So subtracting these values, we will get 0.51. Now remember that delta y is the actual change in the function value. So it's the actual change in the y value using f of x. All right, now what we're going to do is compare that to what we get when we calculate dy. Now dy is defined to be f prime of x dx. This is the differential of y. So that means we're going to need to calculate f prime at 2 times dx, which we know is 0.1. Now, in order to calculate f prime of 2, that means we need to know who f prime is. Remember, f of x is x squared plus x plus 1, so then f prime of x is going to be 2x plus 1, and then f prime of 2, which is the value that we need, is going to be 2 times 2 plus 1, which is equal to 5. So now we can substitute that value back over here in our equation for dy, and we get 5 times 0.1, which is 0.5. Now this is the approximate change in the y value using the tangent line. And this is what we refer to as the differential. The approximate change is 0.5. The actual change was 0.51, so they're actually pretty close to each other. For this value of delta x, meaning a small change is only 0.1, the tangent line approximation is going to give us a pretty good approximation for the change in the function value. In this section, we will be calculating differentials. Now remember, the differential of y is defined to be f prime of x dx. So in this example, where we have to find the differential of each function, in part A, we're given that y is equal to x squared. Now what you do is just first find the derivative. So if we take d by dx of both sides, the left-hand side would be dy dx, and the right-hand side would be 2x. Now this is the derivative form. And then to put it into differential form, all we have to do is take f prime and multiply it times dx. So you can think of this very algebraically, of we're going to take this dx and cross multiply it up. That's how you can think of it in your mind. So then dy, the differential, is going to equal 2x dx. And this is the differential form. In part B, we have that y is equal to x sine of 3x. Then finding the derivative with respect to x, we would have dy dx is equal to, now over here on the right hand side we have a product, so we will have to use the product rule, f prime g plus f g prime. The derivative of x is 1, and we take that times sine of 3x plus f, which is x, times the derivative of sine of 3x, which would be cosine of 3x, and then of course the chain rule tells us we have to take that times 3. So dy dx is equal to sine 3x plus 3x cosine 3x. So this is the derivative form. To put it into differential form, just think of it as cross-multiplying up the dx, and we would have dy is equal to sine 3x plus 3x cosine 3x times dx, and this is the differential form. In part C, we have y equals the quantity x squared plus 1 over the quantity x cubed minus 2, so we know that we will need to use the quotient rule, which is f prime g minus f g prime over g squared. So taking the derivative of the left-hand side, we get dy dx is equal to, on the right hand side we have to take the derivative of the top, which would be 2x, times the bottom, which is x cubed minus 2. Then we have to subtract f, which is the numerator, x squared plus 1 times g prime, which is the derivative of the denominator, 3x squared. And then we have to put that over the denominator squared. So the quantity x cubed minus 2 squared. Let's simplify. Distributing on this first term, 2x times x cubed is 2x to the 4th. Then 2x times a negative 2 means we need to subtract 4x. For this second term, we have a negative 3x squared times x squared, so we will subtract 3x to the 4th, and then we have a negative 3x squared times 1, so we will subtract 3x squared, and our denominator remains the same, the quantity x cubed minus 2 squared. We continue to simplify. Combining like terms, we have 2x to the 4th minus 3x to the 4th gives us negative x to the 4th. Then we have minus 3x squared. And then finally, minus 4x. Our denominator is still the quantity x cubed minus 2 squared. Now here we can factor out a negative x. So negative x times the quantity. From the first term we would get x cubed. From this second term we've already factored out the negative, so this becomes plus 3x. And from this last term, once again, we've already factored out the negative, so this becomes plus, and it's 4. In the denominator, we still have the quantity x cubed minus 2 squared. Now this, dy dx equals this quantity, is the derivative form. And to put this into differential form, just think of cross-multiplying this dx up to the other side. So then we would have dy is equal to negative x times x cubed plus 3x plus 4, close that parentheses, and then in the denominator we have quantity x cubed minus 2 squared, and remember this dx had to get multiplied up, so the dx goes here on the end, and this is the differential form. In this section, you will learn to use differentials to estimate a function value. Let's revisit this diagram where we learned that dy, which is the approximate change in the function value using the tangent line, can be used to approximate delta y, which is the actual change in the function value using f of x. So delta y is just the y value of the second point minus the y value of the first point, which is f of x. Now if we add f of x to both sides, that will move the f of x over to the left-hand side. So we could start where f of x plus delta x is isolated here, and then that would equal f of x plus delta y. Now this is an equality, but we could approximate by substituting dy for delta y. Then what we would have is f of x plus delta x is now approximately equal to f of x plus dy. And the equal sign had to change into approximately equals because dy is only approximately equal to delta y. So when we made this substitution, the equal sign changed to approximately equals. Now we have to recall that dy is defined to be f prime of x dx. And we're going to take that and substitute it in for dy. Now we have f of x plus delta x is approximately equal to f of x plus f prime of x dx. And we are going to be able to use this approximation to estimate function values. In this example, we have to approximate the square root of 24.8 using differentials. So then our f of x is going to be the square root of x. which of course is x to the 1/2, because we're trying to find the square root of this value. We're going to need the derivative f prime of x, which would be 1/2 x to the negative 1/2, which is 1 over 2 radical x. We will also need to pick an x value that is easy to calculate a function value, and it's near the number we're trying to calculate, which is 24.8. So we will choose x to be 25, because 25 is the closest perfect square to 24.8. Well, if x is 25, then delta x, which is the same as dx, would have to be negative 0.2, because to get from 25 down to 24.8, we have to take away 0.2. Now I'm going to purposely leave a little space here, and you should too. But what we're trying to do now is we are trying to approximate f of 24.8 by saying that it will exactly equal f of 25 plus a negative 0.2. Now this, we recognize, looks a lot like the formula we just derived, which is f of x plus delta x is approximately equal to f of x plus f prime of x dx. So that means we can approximate f of 24.8 by first rewriting it as f of x plus delta x, 25 plus a negative 0.2, and then we can approximate it by doing f of 25 plus f prime of 25 times dx, which we know is negative 0.2. Now this will be approximately equal to f of 25. Well, if we come back up here to our definitions, f of 25 is going to be the square root of 25, which we know is 5. And we will add to that f prime of 25. Come back up to our definitions. F prime of 25 is going to equal 1 over 2 square root of 25. So that means 1 over this denominator, 2 times 5 is 10. So we know that f prime of 25 is 1 over 10, and then we have to take that times negative 0.2. Then this will be approximately equal to 5 minus, now we know when we're dividing by 10, that means we have to move the decimal place to the left, so this is 0.02, and we can think of it as $5 minus 2 cents is going to be $4.98. It's one way to think of it. So what this tells us is that the square root of 24.8 is approximately equal to 4.98. And if you plug that into your calculator and check it, you'll see that it's actually pretty close. Now you will learn how to calculate differentials using a graph. In this example, we have to use differentials and the graph of f to approximate f of 2.96 and f of 3.1. So we know that we want to do f of 2.96. Now, if we think about this in terms of f of x plus delta x being approximately equal to f of x plus f prime of x dx, then it's all of these values that we're going to be able to figure out from this graph. Now remember, we want to choose an x value where we know exactly what the function value is there. And on this graph, we know that f of 3 is exactly equal to 2 because we have the point 3, 2. So that tells us that f of 3 is equal to 2. And so that gives us an idea that we want to choose x to equal 3 because it's a known function value there. So that means we're going to go f of 3 plus, now we need to figure out delta x. And remember, delta x is always f of x plus delta x minus f of x. So it's that second point, which in this case, the point we're trying to figure out, 2.96 minus the known value, which lives at x equals 3. So if we do this subtraction, we get negative 0.04. And so now we know delta x, which of course is also equal to dx. We can substitute that in, so we know it's negative 0.04, and that will be approximately equal to f of our x value, which we chose to be 3, plus f prime of 3 times dx, which we just said is negative 0.04. So we've got approximately equal to f of 3, which has already been decided. Now we have to plug in for f of 3, which we know is equal to 2. And we need to add to that f prime of 3, which we need to figure out using the graph. Now remember that f prime of 3 is going to be the slope of the tangent evaluated at x equals 3. Now if we look at this graph, here's the tangent line, and it's tangent to our graph at exactly the point we're interested in. So now all we need to do is figure out the slope of this line. And we see that 3, 2 is a point on the line, and we see right here is another point on the line. And we can calculate the slope because we go up 1 and to the right by 2. That tells us that the slope there, remember, is delta y over delta x. So the change in y is 1, the change in x is 2, so the slope is 1/2. So we can substitute that in for f prime of 3, and then we have to take that times negative 0.04. And we've got 2 minus half of 0.04 is going to be 0.02. So then this is going to result in 1.98. So f of 2.96, we now know is approximately equal to 1.98. Now we were also asked to approximate f of 3.1. So I want you to pause the video and try this one on your own. Make sure you do it, and then restart the video when you're ready to check your answer. So we want to approximate f of 3.1, and we know that we want to apply this approximation formula of f of x plus delta x is approximately equal to f of x plus f prime of x dx. Let's bring the graph back up. So we're going to do f of our known x value is the same, 3, plus, now this time we have to calculate delta x as 3.1, the value we're trying to find, minus 3, the value we know, which is positive 0.1. So we put that in here. And we know that will be approximately equal to f of 3 plus f prime of 3 times dx, which is 0.1. So this is approximately equal to f of 3, which we know is 2, plus f prime of 3, which remember that's the slope of the tangent line, which is 1/2, times dx, which is 0.1. So this becomes approximately equal to 2 plus half of 0.1 is 0.05. So then we've just discovered that f of 3.1 is approximately equal to 2.05.